Imagine approaching a thin, gleaming surface, glossy like the back of a beetle. You touch it with a finger and, instead of meeting thickness, you find yourself immersed in a landscape of depth, reliefs, and volumes. You haven't passed through a portal. It's the surface itself that contains everything needed to evoke the inside. This image isn't a stage trick. It's the heart of an intuition that pushed theoretical physics to wonder whether the space we inhabit, with its three perceived dimensions plus time, might, in some profound sense, be the translation of something else, written in a more essential alphabet. The idea arises from where reality is stretched to its limits, black holes. These are natural laboratories where gravity crushes space-time and quantum mechanics whispers that information, however mistreated, is never truly destroyed. When an object falls beyond the event horizon, everything we know about it, positions, energies, quantum states, seems to slip into an irretrievable oblivion. Yet physics, in its finest equations, is reversible. In principle, given complete data about the present, one can reconstruct the past. Here lies the friction. The horizon closes the door, but quantum mechanics refuses the word, lost. The contrast becomes sharper with the result from black hole thermodynamics. Entropy, the measure of the number of microstates compatible with what we observe, does not grow with volume, as it does in ordinary systems, but with the area of the horizon's surface. The formula proposed by Jacob Bekenstein and completed by Stephen Hawking states that the entropy S is proportional to the area A divided by 4 times the square of the Planck length. S equals K_BA, 4L_P squared. A square nail drawn at the Planck scale, where L_P approximately equals 1.616 times 10 cubed to the power of 5 meters, represents a geometric bit of the universe. Each small square of area 4L_P squared is, so to speak, a unit of maximal information. It's a counterintuitive and yet beautiful result. The internal, informational content of a black hole seems to be measured by the skin that bounds it. By studying that very skin, two physicists, Gerard T. Hooft and Leonard Susskind, formulated the conceptual leap we now call the holographic principle. Under certain conditions, all the physics contained in a volume could be equivalent to a theory defined on its boundary, with one dimension less. It's not merely a poetic image. In black holes, nature already behaves that way. The story becomes even more intriguing when we recall that Hawking, considering quantum effects near the horizon, showed that black holes evaporate by emitting thermal radiation. The temperature of a solar mass black hole is minuscule, about 6 times 10 to the power of 8 Kelvin, but not zero, and over unimaginably long timescales, about 10 to the power of 67 years for a solar mass, the black hole could dissolve entirely. If the emission is perfectly thermal, like a hiss of unstructured noise, where does the information of what fell inside go? Thus arises the information paradox. Quantum mechanics demands the unitarity of evolution, yet thermal evaporation promises oblivion. Either the radiation is not truly structureless, or our understanding of spacetime at extreme scales is incomplete, or both. In the 1990s, a technical result lit the first lamp in the fog. Juan Maldacena demonstrated a mathematical equivalence, now known as the ADS-CFT correspondence, between a gravitational theory in a negatively curved space, anti-de Sitter space, with one extra dimension, and a gravity-free quantum theory defined on its boundary, a conformal field theory. It's as though a gravitational volume were perfectly translated into a two-dimensional film of pure quantum information. This doesn't prove our cosmos works that way. Our observed universe seems closer to a de Sitter geometry, with positive curvature on large scales, but it shows that holography isn't a metaphor. It's a concrete possibility in the repertoire of mathematical physics. Moreover, within ADS-CFT, tools have emerged that seem to speak the language of information, like the Ryuta-Takayanagi formula, which links the entanglement entropy of a boundary region to the minimal surface in the volume. The boundary knows how entangled it is with its interior, and that measure of entanglement is geometry itself. To experts in quantum information, this sounds familiar. The invisible order of entangled states isn't an addition to space, it's the fabric from which space can emerge. This perspective has redrawn the information paradox in subtler terms. Don Page calculated how the entropy of black hole radiation should evolve if evolution is unitary. It increases at first, peaks halfway through evaporation, the Page time, then decreases to zero when everything has escaped. The resulting Page curve is now reproduced in controlled models through holographic techniques and new ideas like quantum islands, in which portions of a black hole's interior become, from an informational standpoint, part of the external space. It's an alien yet precise language. The where of information no longer naively coincides with geometric where. What matters is how entanglement redraws the map. Other clues align with this view. The scrambling time. How quickly a black hole disperses minute perturbations into a tangle of correlations, appears to be among the shortest possible in quantum theory, about beta 2 pi lane s, with beta related to the inverse temperature. Models like the Sachdev-Yee-Kitaev system, a set of randomly interacting fermions, reproduce quantum chaos phenomena and reinforce the intuition that certain aspects of gravity are, in fact, aspects of highly entangled information. Even bold conjectures like equals EPR, which suggests a link between Einstein-Rosen bridges, non-traversable wormholes, and entanglement correlations, hint that the glue holding space together is not a distance measured in meters, but the structure of quantum correlations. And yet, stopping at slogans would be a mistake. Holography doesn't speak of concert illusions or phantom galaxies projected on a screen. When we say that three-dimensional information can be encoded in 2 dimensions, we are not diminishing the reality of the space we traverse. We are describing a dual representation, 2 languages telling the same physics. If the fundamental grammar is bidimensional, the three-dimensionality we experience is no less real than the taste of water compared to the arrangement of its molecules. It is an emergent, robust, measurable phenomenon. Under certain conditions, the 2 descriptions are as equivalent as the statistical mechanics of billions of particles and the thermodynamic laws of a gas. Near horizons and cosmic limits, the bookkeeping of information ceases to follow volume and begins to listen to area. At this point, it's worth pausing the frame over a few numbers. The Planck length defines a scale at which quantum gravity can no longer be ignored. The square of this length, about 2.6 times 10 to the power of 7 square meters, enters the black hole entropy formula as the elemental unit of area. A black hole with a Schwarzschild radius of 3 kilometers, roughly corresponding to a solar mass, has a horizon with an area of about 10 to the power of 8 square meters. Divided by 4L_p squared, it yields an astronomical number of possible microstates. A staggering wealth of information stored on the surface. If the horizon grows, the memory register expands. If it shrinks, that memory is released back to the external world in the form of subtle correlations within the radiation. This is where holography aspires to bring unity. The radiation would not be a random hiss without biography, but a cryptic, extraordinarily complex record of what happened beyond the boundary. The frontier between speculation and calculation shifted precisely because of an idea akin to quantum information science: the link between gravity and error-correcting codes. Certain versions of the holographic correspondence behave like codes that redundantly encode information so that it can be recovered even if part of the boundary is damaged. The notion of the entanglement wedge, the portion of the bulk that can be reconstructed from a region of the boundary, formalizes this intuition. In more narrative terms, not every pixel of the boundary guards the secret of the interior, but specific groups of pixels, properly combined, can reconstruct entire rooms of the volume. This redundancy explains why information isn't as fragile as we once thought, and it also breaks the naive intuition that every point corresponds to one and only one counterpart. In this view, space itself is the diagram of the correlations needed to reconstruct the underlying degrees of freedom. The question, where has the information gone, thus takes on a new meaning. It is wherever you can reconstruct it, not where you had imagined it. If we turn back to our cosmos, the limits of this map quickly appear. The ADS-CFT correspondence has been verified and used in geometries with negative curvature, while the accelerated universe we measure through supernovae and the cosmic microwave background appears to resemble a de Sitter space, not an ADS one. There are proposals for a DS-CFT correspondence, more conjectural and less complete, in which the holographic boundary lives at future infinity, but we are far from having a mathematical version as rigorously controlled. Even so, holography has already fertilized unexpected territories. It has suggested a relationship between the amount of entanglement and the amount of space. It has provided tools to visualize how certain geometries emerge from networks of correlations. It has allowed techniques from quantum field theory to be imported into gravitational domains, and vice versa. Bold conjectures like complexity equals volume, or complexity equals action, which link the computational difficulty of preparing a quantum state to geometric quantities of the black hole, or building bridges between once distant worlds. What is difficult in terms of quantum circuits seems measurable in meters or in Lagrangian integrals. In this scenario, it is natural to ask, how much of this is true, and how much is brilliant mathematics with little grip on reality? Caution is required. We have no direct measurements proving the holographic nature of our universe. Occasionally, bold but uncertain experimental proposals emerge, such as the idea of holographic noise in ultra-sensitive interferometers. So far, there is no consensus on any signal. On the other hand, theoretical physics abounds with ideas that began as mathematical correspondences and later became concrete physical tools. Holography does not yet claim to be a theory of reality. It is a lens that aligns gravity, information, and quantum mechanics into a single image. And the fact that this image works so well in controlled settings is, in itself, remarkable. There is a difference between saying, "We live in a hologram," and saying, "Nature admits equivalent holographic descriptions under certain conditions." The first is a clever phrase, the second, a research program. If we broaden the focus, the story of black holes continues to simmer. The information paradox is not an isolated castle. It intersects with the proposal of black hole complementarity, which suggests that an outside observer and one falling inside can tell different yet consistent stories without contradiction. And it collides with the firewall paradox, an extreme hypothesis proposing that the smooth fall through the horizon might be replaced, for quantum consistency, by a wall of destructive energy. Many believe holography and bulk reconstruction from the boundary soften the firewall, others remain skeptical. These are living debates, and the language of information, entanglement, codes, complexity, has become the lexicon in which they share common ground. If it is true that entanglement stitches space together, then tearing it apart violently could carry a tremendous energetic cost, making firewalls difficult to sustain. Yet it is honest to admit that the issue is far from settled. There is also a philosophical echo worth hearing. If space and time are not primitive ingredients but emerge from a web of quantum relations, we may find ourselves treating reality like a novel in which the plot, the interweaving of dependencies, precedes the setting. This is no poetic license. When the entanglement entropy of a boundary region determines the area of a surface in the bulk, the setting is literally computed from the plot. In certain models, by drawing tensor networks, graphs where nodes represent transformations and edges represent shared degrees of freedom, one can print a portion of space with controlled geometric properties. It's not the physical space you see from your window, but it tangibly illustrates what it might mean for space to emerge from information. If this approach is correct, then many geometric quantities, volumes, areas, distances, are shadows of informational ones. The laws of dynamics could then be expressed as rules about the flow of entropy and complexity, with gravity as an entropic force, or more subtly, as a constraint on how quantum connections can reorganize. There remains one misunderstanding to be carefully untangled. Speaking of holography does not mean claiming that we live in a simulation. A simulation is an artificial implementation of physics inside a computer. Holography is a dual description of the same physics, wherever it exists. If the universe admits a two-dimensional grammar, it is no more fake than describing a spiral in polar coordinates makes it unreal. And there is no reason to fear that this diminishes the world's substance. The solidity of a table, the curvature of a gravitational lens, the spectrum of an atom do not depend on the metaphor we use to describe them. They depend on relationships that, whatever their foundation, manifest with astonishing regularity. If someday we discover a holographic formulation relevant to the accelerating cosmos we observe, it will be because that grammar produces predictions more precise or more elegant than alternative ones. Not because it erases, with a single dramatic twist, what already works. Looking ahead, the path is twofold. On one side, the mathematics of ADS, CFT continues to offer a testing ground for increasingly refined ideas, quantum islands, new entropy calculations in geometries with non-traversable wormholes, links between quantum chaos, scrambling times, and universal limits on information diffusion. On the other side, cosmologists seek a holographic version compatible with the cosmic horizon and the observed arrow of time, perhaps reinterpreting the cosmic microwave background or large-scale structure growth through a boundary dictionary we have yet to write. In between lies the creative electricity of dialogue with experimental quantum information science. Ever larger quantum computers now allow conceptual miniatures of holographic ideas to be tested, simulating laboratory black holes, where information enters, scrambles, and, if the code is cleverly designed, can be partially recovered. Experiments like these do not solve the universe, but they educate intuition, and often intuition, once well nourished, is what glimpses the next possible path first. All this brings us back to the beginning, to that gleaming surface that promises depth. If the ultimate laws of nature are indeed written as a code on the boundary, we will discover it through the patience of well-crafted work, controllable calculations, coherent theories, and comparisons with precise observations. In the meantime, holography already gives us a precious message, that gravity and information are not separate worlds, but faces of the same enigma. Surfaces matter more than we imagined. Entanglement is the lifeblood of space, and black holes, those objects once thought to devour everything, reveal themselves as masters of accounting, parsimonious enough to inscribe their entire content on the skin, Planck square by Planck square. There's no need to strip the world of its reality to recognize that there may exist a deeper way to tell its story. It's enough to admit that sometimes the inside is, surprisingly, all on the outside. If you've made it this far, it means you love curiosity as much as we do. If this journey has intrigued you, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes the difference. Until the next exploration.